Professor, I think you're muted.
Thank you. Sorry about that. Okay. This, I thought I unmuted and then I clicked it again, maybe. Can you hear me now?
Yeah, it's good now.
All right, thanks. So it covers sections 4.6, 5.3, and 5.4. Okay. It's probably the most theoretical of all the tests that you're writing this semester. So it'll be a little careful about all the, definitions and some of the connections that these things make with each other. Okay. I'll come back to the invertible matrix theorem once more after I finish off these two. Okay, so in particular, this was about span of vectors. Okay, so you say the W is in the span of some vectors, say v1, v2, v3, up to vn if the system c1, v1 plus c2, v2 plus c and vn equal to w is consistent. In other words, you should be able to write this vector w as some kind of linear combination of these vectors here, okay, with possibly some of the coefficients being equal to 0. That's okay, but this linear combination should be possible. So if it is consistent, you can always find the constant c1, c2, c3, and so on. So don't forget to use the given vector, otherwise there is no point. Okay, some students, they just make a matrix out of c1, c2, and so on, and they forget about w. Okay, that is not going to be useful. W is part of the process. Okay. So that was the main part of 5.3. We're also talking about null space, but I think that's mostly a modification of what you already did in chapter 4. Okay. Yesterday we started talking about linearly dependent and independent vectors. So when you say that a set of vectors, say S equal to v1, v2, v3, vn, okay, these are linearly independent if the only solution to c1, v1 plus c2, v2 plus dot c and vn equal to 0, okay, is the solution c1 equal to 0, c2 equal to 0. They kind of look alike, but these have two completely different objectives. Okay, in the first case, you are trying to see if this vector can be written as a combination of those vectors there. The second case, you're trying to see if these vectors themselves are related in some way or the other. Okay. So don't confuse the two. In one case, it's a non-homogeneous system. That is why there is a question of consistency there. Second case, we are solving a homogeneous system, so there is absolutely no question of consistency. It's a question of, do we have free variables or not? This is homogeneous. So if this is the only solution, that means there are no free variables in the system. Okay. All the variables are basic, but if there is at least one free variable, that means the vectors are linearly dependent. So linearly dependent if there is at least one free variable. That free variable will help you establish a relationship between the vectors. Okay, you could solve for c1, c2, c3, and so on, and give some values which are not exactly equal to 0. So at least one free variable. And that is where you could write a linear combination that is equal to 0, okay, which is what the textbook says it's vanishing. Okay. But in some cases, you could answer this without doing any calculations. So the shortcuts that we discussed yesterday were the following. If you do this carefully, this is a very good time-saving technique. One, any kind of visual inspection of the vectors can give you some idea. Okay. So for example, if the sum of 2 or 3 vectors gives you the 4th vector, then of course those vectors are linearly dependent. Okay. Second one, if there are, forgot in which order I wrote it yesterday, but I'll try to write everything here so you could kind of match with what I wrote in the last lecture. If we have m vectors in Rn, and if m is strictly greater than n, so we have more vectors than what we need, then those vectors are linearly dependent. Okay. You don't have to do any calculations there. It's a statement that you can use without any proof. I think the most important one is number 3. If you have n vectors in Rn, so the number of vectors and the number of components of the vector are the same. And if the determinant is equal to 0, then what was the statement? Can you remind me? The vectors are linearly dependent or independent? Or is it going to depend on the weather? No. It's okay to just flip back your notes and make sure that we are all agreeing on the same thing here. Linearly then dependent. Okay. So if we have n vectors in Rn and the determinant is equal to 0, the vectors are linearly dependent. Make sure these are written correctly. Okay, don't flip those two things without making the corresponding changes. And I remember what I forgot here. If the list of vectors has a 0 vector, then they are linearly dependent as well. In the past, I've seen students, they'll say, oh, the 0 vector is there, so they are linearly independent. It's probably because they have written it wrong or they are distracted. So just be careful when you're writing these. Okay. So I've made sure that all these things are written for the linearly dependent case. So if you're changing anything, you have to be careful. Of course, there is no shortcut if m is less than n. That is when you have to do that calculation. Okay. REF and check for free variables. If there are no free variables, end of story. Okay, they are linearly independent. If there are free variables, then linearly dependent. And towards the end of the lecture, we started talking about linear dependence of functions. And if you have, say, f1, f2, f3, fn, all these are functions which are many times differentiable. Okay, so n times differentiable, for example, then you can write the Wronskian of this as the determinant whose rows are just the function, first derivative, second derivative, and so on. So it's f1, sorry, f2, f3, fn, f1 prime, f2 prime, f3 prime, n prime, and so on. Okay. It's a pretty scary look if you write all the n rows, but then we mostly do with 2 or 3 functions, so it's not that bad. Okay. If w is equal to 0, that kind of makes use of this concept here. Okay. Shortcut number 3. So if w is equal to 0, then the functions are linearly dependent. And if w is not equal to 0, when I say not equal to 0, just for one value of x, that's all that is sufficient, then this set of functions here are linearly independent. Only got time to do one example, so I'll do a couple of examples more with Wronskian just to make sure that that's clear. But it's just it's just a very basic kind of test. It does not tell you how those functions are related if the functions are linearly dependent. Before that, you have to sit down and make some calculations by yourself. So those are the main conceptual parts of 5.3 and 5.4. Okay. Once again, the REF or REF, all that stuff is just part of the process, but that is not the key idea here. The key ideas are these things. Okay, I don't know if you already got a chance to do the homework. Did you have any questions about any of the questions in the homework or anything? Okay, so let's do two more examples with Wronskian. I'll do the first one myself, and maybe you could try the next one. And since I'm going to do the 3x3 case, the Wronskian for a 3x3 system of functions W of F1, F2, F3 is F1, F2. Again, these are functions of X. Okay. Just dropping the notation of F1X, F2X, and F3X. So this is F1, F2, F3, F1 prime, F2 prime, F3 prime, and F1 double prime, F2 double prime. So that is the Wronskian we are going to use in the first two examples. All right, so here is the first one. Check whether the functions x e to the power of x plus e to the power of negative x and e to the power of x minus e to the power of negative x. So those are three functions, f1, f2, f3. Check whether these functions are linearly dependent or not. Probably the only place where we had to do some calculus in this particular chapter. Okay. All right, so let's write the Wronskian for this. So this is going to be x e to the power of x plus e to the negative x and e to the power of x minus e to the power of negative x. The derivatives would be 1 e to the x minus e to the power of negative x. This would be just that because of the negative in the exponent term. Okay, there's a chain rule, you know, all that stuff. This would be 0 e to the x plus e to the negative x. You can expand this along the first column because that looks kind of easy to handle. Okay, but it's your choice. I don't care which one you use. If I use the first column, it's going to be positive, negative, positive here for the cofactors. That's going to be x times its minor, which is this part here. That 2 by 2 determinant, and then you have minus 1 times the 2 by 2 minor of that 8 to 1 term, which is going to be the first row and the last row. Okay, so the question is, whether this determinant is always equal to 0 or something which is not equal to 0. All right, so you can start simplifying this slowly while I clean this up here. That's going to be x times. But if you do the first 2 by 2 determinant, that's going to be e to the power of x minus e to the negative x whole square minus the other one. And the second one is going to be, we just write it out, e to the x plus e to the negative x times e to the x minus e to the negative x minus the other side. Looks the same. Okay. So I hope all of you would agree with me if I claim that this part is 0. Yeah. They look the same to me. I hope I'm okay. Yeah. All right, let's simplify this one. This is going to be e to the 2x minus 2 e to the x times e to the negative x is 1, okay, plus e to the power of negative 2x. And then you have minus, again, a plus b whole square. That's going to be e to the 2x plus 2 plus e to the power of negative 2x. Again, that middle term is just a number because the exponents cancel out. Okay, so these terms cancel here. Those two terms cancel out. Okay. Looks like it's 0, but it's not. Okay, there is a negative 2 here, negative 2 there. That's a negative 4 times this x. So this is where you shouldn't read too much into what you have in front of you. Okay, so negative 4x, it's not equal to 0 for at least one value of x. Well, that is true, right? If x equal to 1, for example, it's negative 4. That's not equal to 0. Okay. That's all we care about. It's none of our business if x equal to 0 makes it 0. That's not our problem. Okay, so don't investigate too much into what's going on in this Wronskian. It tells you some kind of an elimination criterion for the difference between linearly dependent and independent vectors. So might sound a little harsh, but we don't care. If x equal to 0 makes, that is not the point of Wronskian. The Wronskian is just to see if this is, the whole thing is equal to 0 or not. Okay, if there are zeros here and there, that is not our problem. So the answer is that the functions are linearly independent. That's it. Okay. So it's kind of wrong and not necessary to say that the functions are linearly independent if x is not equal to 0. Okay. Again, that is not the purpose of the Wronskian. All right. Any questions on this example? Okay. If you don't, here is one for you to try. Do this carefully because the answer is a little funny. Okay, so sample 2. The first one is just a number, -3. Then the second function is 5 sine square x, and then the third one is cosine square x. So it's a little bit of an exercise for your calculus skills as well. So the question is to find the Wronskian and check if these functions are linearly dependent or not. Looks could be deceiving. It might look like they're linearly dependent or independent. I don't know. Okay, so you have to really do this and see what happens. Take a few minutes, write down the derivatives. You might want to use some chain rule and product rule. The 2 came from this a square plus 2ab plus b square, or minus 2ab plus b square. And the ab term is going to be 2e to the power of -x times positive x. That's 1. Luckily, I know it's kind of sitting right next to that projector. So, okay. So I've done the hard part for you. You have to do the easy part. Hope it's not too much to ask you what's the derivative of sine square x. What do you think? Just going to write something and let me see if you agree or disagree with me. just left some space in case I'm wrong. What do you think? Yeah. Okay. All right. So that's just basic chain rule, right? The derivative of the inside function, which is cosine x for the first one, sine x for the second one. And some of you might identify this as sine of 2x. You don't have to. Now, the next term is going to be even more crazy. So that's because of the product rule here. The derivative, yep, this one, sure. So let me make some room. That last one should be a negative. Okay, now product rule. That's going to be, let's keep that 10 outside. That's not going to help us anyway. Times sine square x, that's sine x times the derivative of cosine x is negative sine x, negative sine square x. Plus cosine x times the derivative of sine x, which is just cosine x. Okay. Unfortunately, it's a minus here, so it does not really simplify into anything nice. Okay. And similarly here, let's give the negative to outside. Product rule, cosine x times the derivative of sine x, it's going to be cosine square x. And then sine times the derivative of cosine, which is negative sine. So that is what you get. Once again, this is not equal to 1. Okay, that's if you really want to write something that's cosine of 2x, but it's not 1. Okay, now let's expand it with respect to the first column because it's got a couple of zeros here. Okay. So there is nothing much to do in terms of the sign. It's just going to be negative 3 times this 2 by 2 minor here. So instead of writing it as a determinant, I'm just going to evaluate it right away. So negative 3 times this 2 by 2 part here, that's going to be negative 20 sine x cosine x times cosine square x minus sine square x. The product of those two terms. Then you have a minus negative 20, that's going to be plus 20 sine x cosine x times this cosine square x minus sine square x. So there's a negative 3 multiplying it outside. So what? Okay. What is this equal to? I know it looks pretty hideous, but if you look carefully, what is that equal to? It's a 0, yeah, because you have negative of this plus the positive of the same term, that's equal to 0. Now that is what it means by saying those functions are linearly dependent. Okay. If the Wronskian is equal to 0 and nothing else, so the conclusion is that yes, these functions are linearly dependent. Now, how are they related? It's a little bit difficult to see what exactly the relationship between a number and these functions are. Okay, but if you know some high school trigonometry or some middle school trigonometry, you could probably do some manipulations. You don't have to. Okay. So if you're curious about what exactly is going on between these three functions, if you name this as f1, f2, and f3, let's just do f2 plus 5f3. Anytime there's a cosine square and sine square, I'm always curious to know if I can get a 1 out of it. Okay. So this would be 5 sine square x plus 5 cosine square x. That's just 5. So we have F1 equal to -3, F2 plus 5, F3 equal to 5. Okay. Now it's easy to manipulate to get a 0 out of these two terms. Right? So if you do, I don't know, -5/3 times F1 plus F2 plus 5 F3, that's equal to 0 because -5/3 times, or 5/3 times F1, that is -5 plus +5 is 0. But that takes some careful observation of what is going on, and that's what Wronskian is not able to do. Okay. It cannot get you those coefficients C1, C2, and C3 based on this determinant. It just tells you that it's equal to 0. So to do that, you have to kind of sit down and work your way through, which I don't expect you to do. But in case you are curious why they are linearly dependent, that's because of this precious relationship here. Okay. All right, so again, it's up to here that I'm expecting for tomorrow's test. Okay. Now that hopefully all of you are comfortable with the concept of linearly independent vectors, let me just revisit the invertible matrix theorem once more. I told you this will keep coming back to us. So the invertible matrix theorem. The reason I'm writing this so many times is so that you kind of get used to the statements of this. Okay. A small amendment to this, so revisited. Because we got a shortcut now to decide about linearly independent vectors, we could add that into this. Okay. So if A is a n by n matrix, and let the determinant of A be not equal to 0, you can always flip it around. Okay. If you know what you're doing, if somebody says, so what happens if the determinant is equal to 0, all the statements are negated. Then A is invertible. The rank of A is n. Both Ax equal to B and Ax equal to 0 have unique solutions. Okay. To some extent, we know what the unique solution is. For example, for this one, it's going to be x equal to A inverse times B. And for this one, it's going to be x equal to 0. Okay. Second one is even better because we know what exactly we get. Okay. Number 4, here is a question for you. How many free variables do we have in this? I'm expecting a number like 0, 1, 2, 3, 4, 5. How many free variables do we have? Just 0. Okay. No free variables. If the determinant was equal to 0, there's at least one free variable. We don't know the precise number because we don't know how the matrix looks like. Okay. No free variables. How many basic variables do we have? Look at the size of the matrix. How many basic variables do we have? N. Okay. Everything is accounted for. It's either a basic one or a free one. Okay. If it's not free, it's basic. Number 5, A is reducible to the identity matrix, which is sort of equivalent to this one, right? A is invertible means you reduce it to the identity matrix. Number 6, the columns of A are linearly I want you to finish the sentence. The columns of A are linearly. Anybody who wants to say the answer online, just unmute and say linearly what? This is what you should look at. Okay. So 50-50 chance when it's either dependent or independent. What do you think? Independent. So if you make that equal to 0, everything flips over. Okay. We cannot get a precise answer for number 2, though. It's just going to be less than n. This is going to be at least one free variable. So there are some ambiguities that comes with determinant equal to 0 for this list of statements, but everything has to negate. Okay. So this is the latest addition to this theorem. All the other things have been mentioned multiple times. So there are different ways of asking this. One way is, find the values of k, where if the vectors 5, k2, 3, 8, k, and k0, 0. So it's a set of 3 vectors are linearly independent in R3. So in other words, there should be no case or cases of k where those vectors are scalar multiples of each other. A lot of students look at these vectors and say, oh, there is no way that they could be scalar multiples, so it works for all values of k. Maybe because they think these numbers are all kind of prime numbers here, okay, or whatever reason. But you don't know that, okay. Unless you really do this, we don't know if those vectors could be linearly dependent or independent or whatever. Okay. So how do you do this? Any thoughts? The first step is a critical step. After that, it's calculations. How do you do this? Anybody online wants to try this? Just tell me how to do this. We'll do the problem. Set k equal to 0 to get the, well, setting, I don't know if k equal to 0 is going to help, okay, because maybe k equal to some other number might be the key. Yep, set the determinant and set that equal to 0 or not 0. Okay. This is all based on this theorem here. Please don't take your eyes off of the statements of the invertible matrix theorem. Okay. Set the determinant. In this case, linearly independent, which means that it should not be equal to 0. It's the same thing you do for if the rank was equal to n or the matrix is invertible. Okay, it's the same process. You set the determinant not equal to 0. So that's a much more straightforward process than plugging in numbers and trying it, because otherwise there's no end to this question. We'll just keep on trying numbers. You don't know. All right, so let's do that. So it's a 3 by 3. You can only do this if there are enough number of vectors and the same number of rows. So it has to be n vectors in Rn. Okay. If there's a fourth vector, then we are in trouble. So 5 k2 3 8 k k0 0. Once again, the question is asking for linearly independent vectors, so the determinant is not equal to 0. You can expand this along which one? You can expand along any row or column, which is the easiest here. Third column. Yeah. So again, don't forget the k here. Okay, so it's going to be k times Ka2k. Not equal to 0. So there's some minor algebra here. So it's k times k square minus 16 not equal to 0. I hope all of you would agree that for this to be true, k must not be equal to 0, k must not be equal to 4, and k must not be equal to -4. So one of the values that you said there was actually true, that k not equal to 0 is something I have to avoid. Okay. But to get these two answers here, okay, there is no other way than to set the determinant equal to 0 or not equal to 0. Okay. So please don't forget the central idea of these kinds of problems. Okay, so don't try to do too many unwanted things and waste your time. Just go into the determinant straight away and based on the condition, either set it equal to 0 or not equal to 0. Okay, so that is the official end of section 5.4. Okay. Do you have any conceptual questions about anything we did here? So up to here for test number 5. It's going to be a little bit of a different kind of test because of all these theoretical concepts. Okay, so if you know some of these things, you could finish the test within 20-25 minutes. Otherwise, it's going to take forever. All right, so that brings us to the last section of chapter 5. Is probably the central idea of linear algebra, the concept of basis and dimension. Okay, that is what really gives some nice structure and shape to other parts of mathematics. Okay. Gives a very clear definition about how things should play around and how things are defined. I'm pushing this to test number 3 just so that you don't have to have too many conceptual questions on the same test. So test number 6. Sorry. I've never done 6 tests in my classes, so it's a bit unusual when I say test number 6. Okay. It's always test 2 or 3, which is the maximum. All right, so let b equal to b1, b2, b3 dot bn be vector space, which at the risk of repeating myself many times, okay, these vectors could be functions or matrices or vectors. Then a set of vectors let's call it as S, forms a basis for V. If there are two conditions, one, the set of vectors in S must span V. Hopefully all of you make the connection. Span means you should be able to write any vector in V as a linear combination of the vectors in S. Okay. So any vector V must be, when I say equal to, it must be able to be written as a linear combination of the vectors in S. So that's the first condition. The second condition is that the vectors in S must be linearly independent. So condition 2. Vectors in S must be linearly independent. So not only that, you should be able to write every vector in that vector space as a linear combination. Okay, they cannot be just multiples of each other. They have to be completely different vectors. So you're not expected to do any proofs or anything based on this. The main idea here is to understand what this means. Okay, so there are some simple examples to make this clear. These are examples which are kind of non-technical so that you could make connections with what you hopefully already know. Okay. So take your XY plane, R2. That's my favorite place, okay, because I know how it looks like. Got x-axis, which is horizontal, y-axis vertical. And I've talked about this before. If you take the unit vectors 1, 0 and 0, 1, then these two vectors span R2, okay, because if you take any vector here, AB, that can be written as a linear combination of this and that. So AB is equal to A times 1, 0 plus B times 0, 1 for all values of A and B. It doesn't matter which quadrant you're in. If you want something like -3, -13 somewhere here, okay, that's -3 times the first vector minus 13 times the second vector. That is what it means by saying these two vectors. So V1, V2 spans R2. And without a long discussion, we also know that those two vectors are linearly independent because one is on the x-axis or one is on the y-axis. Okay, they are not on top of each other. So 1, 0 and 0, 1 are linearly independent vectors. If you really want to convince that yourself, you could take the determinant of 1, 0, 0, 1. That's an overkill. Okay, that's 1 not equal to 0. You don't have to do all that stuff because those axes are standing at right angles. They are not on top of each other. That's why we say that these two vectors, 1, 0 and 0, 1, forms the standard basis for R2. Because everything in R2 is based on these two, if you think in a nice straightforward way, forms a standard basis for R2. I think at that point you have some kind of an intuitive idea about what basis means. It forms a base for everything. Okay. I'm using the word standard, or mathematicians use the word standard here with the word basis because there are plenty of other vectors in R2 that will serve the same purpose. Okay. These are not the only ones. You can sit here and write an infinite number of vectors which are basis for R2. These are the most attractive ones. So note that there are infinitely many choices for the basis for R2. Here is one example, S equal to 2, -3, 5, 7. Completely random vectors. What's the problem with these two vectors? First of all, I have to position myself to look that way. Okay, and these are not the most natural things to think about. Right? But these are linearly independent. Okay, so if you take 2, 5, -3, 7, the determinant is not equal to 0. And if you spend some time, you could actually write every vector as a linear combination of these two. Okay, it's going to be a struggle, but you can. Okay. So every vector can be written as A times 2, negative 3 plus B times 5, 7. So you have to set up a augmented system and then solve for it. Okay. It's going to work out, but for each point, you have to sit and do this. Do you want to do that? No, especially when you have something as easy as this sitting here. Okay, why do you want to go through all that pain? But in theory, there are infinitely many choices of this basis for R2. So it's just that it's inconvenient. Not only that, your whole perspective of the XY plane would change. Right now, we are standing on a horizontal plane, okay, and with our head standing upright. If you use those two vectors, you're standing in some kind of lopsided plane. Okay, you don't want to do that. Okay? Because the vector 2, negative 3 is somewhere here. It's x2, negative 3 is here. Okay. And 5, 7 is here. Imagine if this was your x-axis and that's a y-axis. You could do it, but then you have to walk like this. Yeah. So that's why you always stick to the standard basis and not some weird basis. Now, can you tell me the standard basis for R3? Standard basis, not a inconvenient, painful basis, but what will be a standard basis for R3? Can somebody online try this? I think we have mentioned this before, so it's just a repeat. So either all of you are sleeping, or all of you are not there, or somebody is going to give me the answer. All right, there you go. That looks pretty nice without the commas, actually. 100, 0, 10, and 0, 0, 1. Yes. So the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's the standard basis for R3. Once again, you can put random numbers in there and create your own basis and make your life more painful. Okay. What would be a standard basis for the set of polynomials of degree less than or equal to 3? In other words, what are the basic building blocks of polynomials of degree less than or equal to 3? Can somebody tell me? So a linear combination of 3 or 4 things should construct all polynomials of degree either equal to 3 or less than 3. Any answers? All right, 1xx square. So since it's less than or equal to, you can probably go one more. Okay, so 1xx square and x to the power of 3. So, but yeah, that's good. Because I have less than or equal to, not just less than 3. And that's a standard basis. You could have weird polynomials to create this. That'll be more painful. Okay. And lastly, what will be a standard basis for all 2 by 2 upper triangular matrices? So if you have 3 2 by 2 matrices, you can create all of the upper triangular 2 by 2 matrices in this universe. What are those three matrices? I know this is probably difficult to type, so you might have to either unmute and say, or maybe somebody here can tell me this. I'll write the first one, 1 0 0 0. Upper triangular matrix look like this: A, B, 0, C. So can you tell me the next one and or the next two? Is somebody giving an answer online, or I don't know, I hear some noise. Yeah. 0 1 0 0, good. And good. Okay. So any combination of those three matrices, which are all 2 by 2, will generate this matrix here. Okay. For different values of A, B, C, including them equal to 0. That's fine. Okay. So that's a standard basis. Again, you could have other random 2 by 2 matrices doing the same thing, but with more pain. Okay. So in all these, there is a finite number of vectors in the basis for all these vector spaces. Okay. So in this case, the vector space was the set of all 2 by 2 matrices. That is your V, and this is your S. In this example, S is this set, and V is the set of all polynomials of degree less than or equal to 3. Okay. So there is a big set and there is a smaller set, which is defining the bigger set. So the word dimension, which you have probably used loosely in the past, okay. So for movies with a 3D, what does that D stands for? Dimension, right? So the dimension of a vector space is the number of vectors in the basis of the vector space. So it's a number that you use to count. Okay? So you should be able to count 1, 2, 3, or 1, 2, 3, 4. Okay? So it's a number of vectors in the basis of that vector space. Okay? Let's call this V, basis of V. So that should probably clear the mystery as to why you call R2 as two-dimensional, because 1, 0 and 0, 1 was the standard basis for R2. So it's two-dimensional because the 2 is standing for the dimension. Okay. The basis was 1, 0, 0, 1. Okay. So there are 1, 2 vectors there. So the dimension is 2. Similarly for R3, it's dimension 3 because there are 3 vectors in the basis for R3. Shouldn't have erased this, but that might sound weird. Now we can make some sense out of this one. Okay. The set of polynomials of degree less than or equal to 3 has a dimension of 4. But that doesn't mean it's a 4-dimensional space. Okay. So that word dimension is more abstract in those kind of situations there. So the dimension of set of polynomials of degree less than or equal to 3. You cannot get anything for degree equal to 3 because that is not a vector space. Okay. Degree less than or equal to 3 is equal to 4 because there are 1, 2, 3, 4 vectors there. But nobody says that polynomials are 4-dimensional because It's not a pictorial thing at that point. Okay, this one is more pictorial because R2 is two-dimensional. And similarly, the set of R 2x2 upper triangular matrices what is the dimension of that one? I kind of erased it, but how many vectors were there constructing the 3? So has dimension 3. That has nothing to do with this 2x2. Okay, we're talking about the dimension in the context of how many vectors were there the basis. Okay. So has dimension 3. And those 3 vectors were one, I shouldn't have erased it, but these are the ones. So don't confuse that dimension with this one. This is the dimension of the matrix. That is the dimension of the vector space. Okay. Now, since we are doing this in a very quick and kind of in a hurried fashion, okay, there are 2 things that I want you to know to do your homework and probably for test number 6. Okay. One is the following. So when you take a proper linear algebra course, you will deal with a lot more crazier things about basis. For now, let's just do what you need to do in this particular chapter. Here is an important theorem, which I'm not going to prove, but any set of n linearly independent vectors form a basis for Rn. Okay, so this theorem is about basis. Okay. It's telling you something which is very useful and important. You can kind of skip the span condition there. That is what this theorem is helping you with. Okay. This is guaranteeing that if those vectors are linearly independent, then span is already taken care of. Okay, that avoids a lot of headache because you don't have to sit and check if the system is consistent or not. Okay, and at this point, I hope we have some method of checking this one. How do we check if there are n linearly independent vectors in Rn? What is the quickest way of doing it? You can't forget this. N vectors in Rn, what is the quickest way? Determinant. So this comes down to whether the determinant is equal to 0 or not equal to 0. If the determinant is equal to 0, then not a basis. If the determinant is not equal to 0, it is a basis. So that's actually one more statement to the invertible matrix theorem, but I'll save that one for the next one. Okay. So tomorrow you can kind of skip the basis part of things because you already have enough on your table. But it's the same thing, right? Basis means in this context, it just means linearly independent vectors because span is already true. So these topics have a slightly cumulative nature, even if you say that the chapter 4 was covered on the last test, chapter 5 on this one, okay, they kind of roll over. So please don't just throw away your notes from the last couple of weeks. So that is one thing, okay, which, as I said, we'll come back to after your test number 5 so that you won't get too confused at this point. The second one, basis and dimension of a null space. I know we are doing the same thing over and over with different names and different shapes and everything, but at the end of the day, you are just taking a matrix A, which is of some size m by n. Okay. The null space is just the set of all the solutions x equal to 0. So you're just solving the homogeneous system. So if it is not an REF, you have to do that first, identify the free and basic variables, okay, and then write it as a span of vectors using the free variables. That's what you're doing in section 5.3. Yeah, and just using fancier words, but you're doing the same thing. Once you do this, you have the answer to this new thing here. These vectors will form the basis for the null space. Null space is one word. So whatever vectors you get here in terms of the free variables, those are the vectors that span the null space. So those are the basis for the null space. And the number of vectors there is the dimension of the null space. Number of these vectors here. Okay. And that is the dimension of the null space. So you're not doing anything new calculation wise. All you're doing is just give it a new meaning or connect the concept of basis and dimension to your solution to the homogeneous system. Okay. There is a small, if you look carefully, there is a small thing you could observe, that the number of free variables must be equal to the dimension always, okay, because you're writing it as a linear combination of vectors using the free variables. Okay. So one quick check is that the number of free variables should always equal to the dimension of the null space. Okay. It's not the dimension of A. Just be careful about what you are writing here. Okay. The number of free variables is equal to the dimension of the null space of A. There is no meaning for saying the dimension of A. Okay. That just says the number of rows and columns, but it's not the same as what you're saying here. But apart from that, all you're doing is just a good exercise with identifying the basic and free variables and writing it out. Okay, that's it. Okay, let me do a quick example, which in some form would be also a good practice for section 5.3. So 1, -2, 1, 3. 1 and 0, 0, 0, 0, 1. So this is an REF of some matrix A. Okay. I'm going to save you some work. You don't have to do any row operations for this. So question number 1. Write the vectors that span the null space of A. I'm just going to write null A just to save some writing. That means the null space of A. This is what you're doing in section 5.3. And question 2, write the basis and find the dimension of the null space of A. That's what you're doing in section 5.5. But both these were also done in chapter 4 because all you're doing is solving a homogeneous system. This is the coefficient matrix of that homogeneous system. All right, can you identify the basic and free variables and get going with this? So in your expert opinion, which variables are free? I hope there are free variables. So which ones are free here? I think they're kind of sitting right next to each other. This one is basic. What do you think about this one? Basic. All right, so yep, so x2, x3, and x4 are free. So let's give some nice names to it. x2 equal to u, x3 equal to v, x4 equal to w. Okay, that kind of already answers this part of the question. The dimension of the null space is 3 because they got 3 free variables. Okay, so if you want to just get rid of that answer, the dimension of some students write dimension equal to 3. Dimension of what? So dimension of the null space of A. Equal to 3, and let's do our calculations and see what those 3 vectors are. Okay, so row 2 gives you x5 equal to 0. Okay, there's nothing you could do with this. And row 1 seems to be the only equation that has got anything alive. So it's going to be x1 minus 2x2 plus x3 plus 3x4. So a lot of freedom there, right? Because only 2 equations. The second equation is practically nothing. So plus 1x5, which is 0, equal to 0. So x1 equal to 2u minus v minus 3w. And in this case, the question is asking for the vectors which are forming the basis. So writing the answer in the vector form is appropriate and expected. Okay. So x1, x2, x3. Is something missing in this? X5. Yeah. Just because it's 0, don't throw it away. We need everything. Just showing some of the mistakes students make when you write the answers. You know, they just pick and choose some variables and keep the others out. They just put everything in here, whether it's equal to 0 or not. You know, you don't have to worry about that. Okay. That's equal to u times 2, 1, 0, 0, 0 plus v times -1, 0, 1, 0, 0 plus w times, I push myself into a corner here. plus W times -3, 0, 0, 1, 0. Okay, sorry about that. I used a lot of space here. So the vectors that span the null space of A are those three column vectors that are standing right there. Okay. So part one, vectors that span the null space of A. You can either just list it one by one, or you could just name them V1, V2, V3. Okay, but there should be some kind of way for somebody else to understand what you mean. So this is the best way to do it. 2, 1, 0, 0, 0. -1, 0, 1, 0, 0, and -3, 0, 0. One, two, three, 4, 5. Those are the vectors that span, because that's a linear combination of those vectors up there. Okay. There is absolutely nothing that is different when you answer part B. Write the basis for the null space, exactly the same vectors. Because basis is a set of vectors that are linearly independent and that spans that set of whatever that represents. So for the null space, those vectors are the ones that are, they are linearly independent, obviously, because 1 is not a multiple of 0, okay, and the 0 is not a multiple of 1. So these vectors are all separate vectors by itself. Because no scalar multiple of any of these vectors will give you the other vector other than 0. So the dimension, of course, is 3 because you have 3 vectors, okay, and that was confirmed by the fact that we had 3 free variables. So the dimension of the null space of A . So if you don't answer it earlier based on the number of free variables, you answer it here by counting the number of vectors here. Okay. Either way, there's only one answer, that is 3. Okay, so that is the official end of chapter 5. Again, for tomorrow's test, you don't have to worry about basis and dimension, though it's nothing really fascinating if you know what span and linearly independent vectors are. But I don't want to push too many things on the day before the test. Okay, that's why we'll keep this for test number 6 along with the more exciting things coming up. So it's the end of chapter 5. So I think we are now ready to do what is required to go back to differential equations. Okay, kind of building a bridge here between two seemingly different parts of math, linear algebra and differential equations, and the connector part is coming up now. So you got all the theoretical background, hopefully. We didn't do a lot of unnecessary proofs or anything. That is a different course in linear algebra. We just kind of barely touch the surface of linear algebra to understand the main concepts. Okay, before I kind of lay the groundwork for the next topic, okay, do you have any questions about this part here or chapter 5 in general? Okay, so I would like to call every lecture as the most important lecture, or most important topic, but whatever is coming up is probably the most important one from a linear algebra lecture. If you are an applied mathematician, like an engineer or a physicist, okay, the next topic is what really makes it worthwhile. So chapter 6. We're going to talk about these creatures for the next 2 or 3 lectures till the end of the semester. So please get used to this. Eigenvalues and eigenvectors. I'm hoping to be done with most of the material we need for the semester by next Tuesday or early Wednesday. I don't think there'll be a lecture next Thursday, okay, because there is nothing to teach that day. Kind of winding down here. The word eigen, if you have seen this this pair of words before, okay, one cannot exist without the other, eigenvalues and eigenvectors. The word eigen stands for principal. So it's something that tells you the main values or the principal values and the principal directions of certain set of points. Okay. These days, these are extremely crucial when you're doing data analysis and machine learning, because it kind of tells you how to avoid unnecessary data and stay along a certain path so that you don't get distracted with millions and millions of data points. So it's a very abstract concept, which is extremely useful depending on what kind of applications you do. But just to motivate you into this one, it's always nice to give some geometric meaning to these things. Okay, so let's consider this matrix A, which is 1, 4, 2, 3. And 2 vectors, V1 equal to 2, 3, and V2 equal to -1, 1. Let me make sure that I got those correct. 1 second. Oops. Oh, sorry, -2, 1. Sorry. You might be thinking, what's the big deal? But we'll see. Okay. So there is a 2 by 2 matrix. There is a 2 by 1 vector. These are all vectors you can easily draw in an XY plane. Okay, 2, 3. And the second vector being -2, 1. So my request to you now is to find the product A times V1 and A times V2. That's a silly thing to ask because you're all experts in multiplying matrices, but can you find A times V1, A times V2, and if you see something worth reporting, okay, let me know. All right, so not going to write all the multiplicative details. I hope all of you know how to multiply a matrix with a vector. Okay, the first row is going to be 2 plus 12, which is 14, and the second row is going to be 4 plus 9, which is 13. So what this operation here is telling you is that you had a vector 2, 3. None of these are drawn to scale. Okay, so don't say that, oh, that is too short or too long. Okay, so that vector is 2, 3, x coordinate 2, y coordinate 3. And this matrix transforms it into a completely new vector somewhere here, say 14, 13. It's far away. What is important to note, or which can help us kind of ignore this particular case, is that this vector 14, 13 is not a scalar multiple of 2, 3. So you can never get a scalar that will multiply 2, 3 and give you 14, 13. What about the second one? So the first row is going to be negative 2 plus 4, which is 2. Okay. And the second row is going to be negative 4 plus 3, which is negative 1. Now let's look at what happened here. Okay, you took the vector negative to 1, which is here. Okay. It's x equal to negative 2 and y equal to 1. Multiplying this matrix, it didn't just send this vector into some arbitrary new direction. Okay, it just took it to an exactly opposite point here. This is 2, negative 1. See the difference between the two cases? In one case, there was absolutely nothing attractive about it. Okay. Second case, we're just lying on the same straight line. Okay, did not go away from this one. This is one of the reasons why if you take a course in machine learning, the first thing they ask you is, do you know about eigenvalues and eigenvectors? Because you're trying to kind of get important things kind of lined up on that particular vector there. Okay, everything else can lie here. Nobody cares. Okay, that one thing has got all the important information. Okay, that is what kind of filters it out. That is why it's called the principal value and the principal vector. Okay, so in this particular case, the product 2 times negative 1 was negative 1 times the original vector, which was, let's say, v2. Okay, so this is negative 1 times v2. The first one, nobody cares because it reads somewhere else. Okay, there's nothing important with this. So that's what we are trying to investigate here. Are there some special values where the direction will pretty much lie on the same line in R2 or same plane in R3, okay, or in higher dimensions? Just don't go away from that hyperplane or whatever you call it, okay, and just ignore everything else. So the question is, can we find non-zero vectors? Let's call it as V, such that you multiply any compatible matrix A. Okay, we are going to look at mainly square matrices, so let this be an n by n matrix. Okay, with that vector V, which is n by 1. In R2, it's a 2 by 1 vector, but in R3, 3 by 1, R4, 4 by 1. Okay. So if you take the product of these two, it's going to be some scalar multiple. That scalar is usually denoted by the Greek letter lambda, okay, times the same vector V, where this is a scalar, and that letter, if you're not familiar, it's just the Greek letter lambda. So I don't know who started the practice of using lambda for eigenvalues, but it is just stuck on. Okay. So our objective is to find these special scalars lambda for which any non-zero vector v would give you this particular case. Emphasis on the word non-zero, because if v equal to 0, there is nothing attractive about this one. Okay. So this is very important here. So if somebody walks to you and says that, from tomorrow onwards, 0 can be included in that one, you should just walk away from there, because that's the most offensive thing you can hear about. Okay. There is one thing that you should remember from today onwards. In all these cases, the vector v should be a non-zero vector by definition. Okay. This can never be equal to 0, because it's equal to 0, it's just 0 equal to 0. Who cares? Okay, so let's write the definition, and then I'll probably postpone the calculations to tomorrow. So definition, let A be any n by n matrix let lambda be a scalar and v be n by 1 non-zero vector. Now, don't get me wrong, there are a lot of people who are trying to tempt you into thinking that it could be a zero vector. Okay, don't fall for it. It's a non-zero vector, right? So if A is n by n matrix, let lambda be a scalar, then lambda is called the, you don't have to write lambda, just the Greek letter lambda. Lambda is called an eigenvalue of A. If A times B equal to lambda times V, and the corresponding vector V is called an eigenvector for this particular eigenvalue lambda. Okay. So starting tomorrow, we'll be doing some easy hand calculations for 2 by 2 and 3 by 3, including imaginary eigenvalues, okay, and see how that will fit into systems of differential equations when we start chapter 7 next week. So all that we're going to do from now on, it's going to be about eigenvalues, so please don't ignore this concept. Okay. All right, that's it for today. And again, tomorrow's test doesn't have anything to do with eigenvalues, so you can just kind of postpone it for the weekend. Thank you.
Thank you.
Thank you.
Thank you. Let me stop recording.